Hi, I'm Gary Thomas, a math professor here at College of Western Idaho, bringing you today some more math help. Today what we're doing is foiling shortcuts. Foiling is a shortcut used in general to multiply simple polynomials like this one. Let me show you first the generic problem. Here what I've done is I have the same thing, except instead of using actual numbers for my coefficients, I've made it generic by using letters of the alphabet. I've just picked A, B, C, and D. And the idea of FOIL, the reason it's called FOIL, is when we multiply these, we know we have to use the distributive property, and we actually use it 4 different times. The first time is with the first terms in these little polynomials. So my AX times my CX is my first, and my AX times my D is the outside, and the BX times B, times the CX is my inside. And then finally, the last combination for the distributive property is this B times this D, and that's the last. And so if we take these letters, first, outside, inside, last, the initials, we get FOIL. And so if I were to FOIL this generic problem, bear with me, it only goes for a minute. We have the F, this is the first, the AX times the CX. AX times CX equals A times C, I've put my numbers in the front, times X squared. And then the O, this is the outside, I have the AX times the D, AX times D. And again, we mathematicians like to put the numbers in the front and the letters at the end. So A times D, and then the X variable at the end. Doing the inside, this is the I. We have B times CX. And this one's friendly enough that the numbers are already there, and there's the variable at the end. And then the L, the last, so that's the B times the D, and that's just numbers, so that one's fairly simple. B, D. And so what you notice in this is this has a degree of 2. It has an X squared. Both of these have X, and the last has no variable at all. So these two, both being X, we can combine them, and this is using the distributive property AD plus BC times X. And if we wanted to write the entire solution, it would be ACX squared plus the AD plus BC X plus BD. And what I'll tell you now is, this is where you should pause the video, copy this into a prominent place in your notes, leave it out on the kitchen table tonight, and when your family members walk by and see what you're studying, they'll be very, very impressed. The truth is, no one does it this way. This is a lot of numbers. This is a formula that shows the technique. It shows that the thing works. But no one would memorize this. I don't have it memorized myself, and I'm a math professor. Let me show you instead how the problem actually is done in practice. So we have the first, we have the outside, we have the inside, we have the last. And the first, we just look at this, and it's 2x times 3x. There's a 2x times a 3x. We know 2 times 3 is 6. You can do the number part, then you can do the letter part. X times x is 6 squared. The outer, this is the 2x times the 7. And again, do the number part together. So 2 times 7, 14. And then there's an x. The inner, the inside, we're doing the 5 times the 3. That's the number part with an x. So 5 times 3 is 15. The last is the 5 times the 7, and that's 35. And again, as usual, we combine these. 15 plus 14 is 29, and then there's an x. And in real life, you can probably do these completely in your head with a little bit of practice. You have to know your times table. That's a requirement for algebra, for any college level math. But you can probably do them. 2 times 3 is 6, and I know the first term is always an x squared. and then I do the outer. 2 times 7 is 14, and I always say it 3 times. I say 14, 14, 14, so it gets in my mind, and then I can remember the 14. Then I look at 5 times 3, 15. I still remember the 14 plus the 15. Here comes my 29. The middle term always has an x as its variable. And then the last, 5 times 7, is 35. And so I encourage you to practice these enough that you can start with the problem and do it entirely in your head and just write the answer. And it looks very impressive, but it's not actually a lot of work. You might be thinking that was a little too easy. They're harder if we have a minus sign in them. So here's an example with a minus sign. And I'll show you there's just a little bit of extra work, cognitive load in your brain, but not enough to make it undoable. So again, the first, well, this is pretty easy. 2 times, there's an invisible 1 there. So 2 times 1 is 2, x squared. And I don't even have to write the separate letters. We do the outside. This is a negative 9 times this invisible 1, so negative 9x. The inside, 2 times 3 is 6, 6x. And the last, 3 times a negative 9 is negative 27. And as usual, the inside, the inner terms, the middle terms combine. So negative 9 plus 6 is negative 3. With an x. And let me give you a little shortcut for this. Whenever you have 2 things with different signs, we're always going to subtract. And I always tell my students, 3rd graders subtract. In algebra, in college, we don't subtract, we add the opposite. And so the idea is if you gave a 3rd grader a problem and you said, hey, subtract 9 and 6, they don't know how to do it. They're always going to say 9 minus 6 is 3. Well, we as grown-ups know that's the wrong answer. What's the secret is that the 9 is bigger. Whichever is bigger, that's the sign you go with. So if someone says subtract 9 and 6, you always do it the 3rd grade way. 9 minus 6 is 3. Then you look at the bigger number, see that its sign is negative. That's the sign of your answer. And so that's all there is to that. So again, no one's going to actually write this. This is just to show you what's going on inside my mind. What you'll actually do is you'll say 2 times 1 is 2, and you know that it goes with an x squared. Then you say outside is a 9, it's a negative, and you say it a couple times to remember to yourself. Negative 9, negative 9, negative 9. Then you look at the 6. You say 9 minus 6 is 3. The 9 is bigger, it's negative, so it's a negative 3. The middle term always has an x. And then the end, 3 times 9, and there's a negative, so we put negative 27. And there's how you would do a problem that's a little bit harder because it has a negative sign in it. All right, we're getting good at this. Onwards and upwards. Let's try one that has 2 minus signs in it. It has one little complication. It means we have to pay attention for just a moment. But actually, this is probably easier than our previous problem because we never have to subtract. All we have to do is add. So here again, our first is 3 times 5. Do the number part. It's 15, and you know it goes with an x squared. The outer has a minus sign. So 6 times 3 is 18. It's a negative 18x. The inner, again, with a minus sign. 1 times 5 is 5, so negative 5x. And then the last, what did the schoolboys in England used to say 100 years ago? Minus minus makes a plus. The reason why we won't discuss. But 1 times 6 with negative, negative, they cancel, and it just becomes a 6, a positive 6. So now when we combine these, the advantage is they're both negative. If you have 2 things that are both the same sign, you don't have to subtract them, you just add them. So 18 plus 5 is 23, and what was that identical sign? It was a negative, and there's an x. So when you're doing this in your head, without writing all this, because we don't need to write this, we say 3 times 5 feels like 15. We know the first term is x squared. We do the outer. It's a negative. We get an 18. The inner, it's a negative. We get a 5. They're both the same sign. We add 18 plus 5. You can say the 18 a few times if you need to, the way I was before. You get 23 with a negative, and then minus minus makes a plus. We put a 6. And that's how easy they are with two negatives. Rubber hits the road. Let's apply these shortcuts to complex numbers, which students have to multiply a lot, and it can be tricky. And I'll show you that it's actually simpler than you think. We need a review. A complex number is a number that looks like a plus bi, and this I here is defined to be the square root of -1, which of course doesn't exist. I actually stands for imaginary. This is an imaginary number because there aren't two values that you can multiply together and get -1. The implication here is that if you did square it, you'd get -1, and that's just a mathematical definition. It's convenient. This A is called the real part, and this B is called the imaginary part for that reason. And because it has a real part and an imaginary part, we call these complex numbers. So there you go with a little background on what a complex number is. Let's look at multiplying two complex numbers together. And my example will be 1 plus 2i times 1 plus 3i. And we don't have x's now, we have i's, which actually makes it easier. We don't have to worry about it. Things will combine in a slightly different way, but we'll still use the same technique of the first, the outside, the inside, and then the last. So here we go. The first, 1 times 1. Well, that's dirt simple. Anybody could do that one. The outer is 1 times 3i, and 1 times 3 again. Do the number part, that's a 3, and then there's an I with it. The inside multiplication is a 2i times 1. Again, 2 times 1 is 2. Do the number part, and then there's an I with it. And then at the end is where it gets a little bit tricky. So our last terms in these two binomials are 2i and 3i. We're multiplying them together. Do the number part. 2 times 3 is 6. I times I is I squared. And we know from the definition of an imaginary number and how complex numbers work that I squared equals -1. So this is 6 times -1, which is -6. So the way all the books will teach you to do this is just how I've done it. We have 1, we have 3i plus 2i, and of course we'll combine those, right? They're both some coefficient number times an I, so 5i. So far so good. And then -6. When we were doing the earlier problems, we were done. But not this, because the 1 and the -6 are both real numbers, and we need to combine those. And so 1 minus 6 is -5, and then the 5i, the imaginary part. And there's our final answer, and you can see that it matches this form, the a plus bi. So there's the real part, there's the imaginary part. I think this takes way too long. Let me show you my shortcut. My shortcut, instead of foiling, I'm going to FLOI. We don't foil, we FLOI. And the idea is the first part gives us a real number. The last part gives us a real number. And we need to combine those. So do those together, and then you can write them down together. And then the outside and the inside, they both give imaginary parts, and we can combine those. So if I FLOI it instead of foiling it, and I'll write down more than I need to, I do the first, it's 1 times 1. I do the last, it's 2 times 3. Here's the trick. The last is always a negative, because there's always going to be an I squared, because the last term in every complex number has an I. So I times I is always I squared. There's always a -1. So multiply these together, 2 times 3, 6, and then write the opposite, -6. And those will combine very nicely. And then the O and I work out the same way, right? The O is 1 times 3, that's a 3 with an I. The I, 2 times 1, that's a 2 with an I. And these combine, and these combine. And we have the same answer we had before. Let me show you how you can do it, because you don't have to write all this down. No one wants to write all this down. You use the FLOI technique. Start with F. 1 times 1 is 1. Say it a few times to get it in your mind. 1, 1, 1. I think I remember it. Now we do the last. 2 times 3 is 6. It's a negative 6. What was the number I remembered? 1 minus 6. I write down the negative 5. Do the outside. 1 times 3 is 3. Say it a few times. 3, 3, 3. I think I got it. Do the inside. 2 times 1 is 2. Plus that number that I just remembered, 3. 2 plus 3 is 5. And it has an I. And you can see pretty much in one step, it feels like one step. I don't write any of this nonsense. I go from the problem to this, and how hard was it? I had to remember a 1, 1, 1, 1, and I had to remember a 3, 3, 3, 3. It wasn't really a lot of work. With a little bit of practice, you can do these really, really fast yourself. We're becoming more and more expert in multiplying these small binomials together, the regular kinds which use FOIL, and now the complex binomials which are a little bit easier to use FLOI because it saves you a simplification step at the end. One of the most common types of multiplications of complex numbers is multiplying two complex conjugates. And if you don't remember what those are, that's fine. You're allowed to forget stuff and learn it a second time. So here's a little recap. The whole idea of this complex conjugate, this is Latin. Con means with and jug means joined. They're joined together. They always go together. You'll find them in problems coming out together with each other. And the idea is if a plus bi, that's our generic complex number, a real part and an imaginary part, its complex conjugate is a minus bi. And it's that simple. There's a plus and there's a minus. Well, yeah, but what if you start with something where there's a minus? Well, then it changes to a plus. The beginning doesn't change at all. Sometimes students make that mistake and they'll want to do something to it. Don't touch it, just whatever's just before the imaginary part, change the sign, and then you have the two complex conjugates, and you can see how they're joined together. They're really good friends because they have so much in common, just this one difference that makes their relationship interesting. So this is a very common sort of problem, and we'll see here shortly why it's so common. It turns out that there's another shortcut that we can take that makes these even easier. You can do them totally in your head. You don't have to write down anything. It's fabulous. So here's an example. We have 5 plus 7i times 5 minus 7i. And I'm going to do this super slow-mo. I'm going to do the whole FLOI technique so that you can see exactly what's happening behind the scenes. And you'll know what's happening behind the scenes, and you know that it's easy, and everyone else will be amazed when you just whip these answers out with seemingly no effort on your part. The idea is the first, well, this is two numbers. This is 5 times 5. A baby could do it. It's 25. The last is 7 times negative 7. What I want you to notice is that these two signs are always opposite. They have to be opposite because they're conjugates. They're plus and minus, or else they're minus and plus. They're always opposite. So you always get a negative, but then there's an I squared, right? And we know that I squared is the same as negative 1. Again, minus minus makes a plus, and so the result of this last step is always a positive. All you have to do is look at the numbers. 7 times 7, it's always a square. If you know your squares, you're good to go. 5 times 5 is 25. 7 times 7 is 49. I really didn't have to do any of this extra work. These steps are just you if you need to understand it. But all you're doing is multiplying 7 times 7. Here comes the outer. 5 times negative 7. 5 times negative 7i. Here comes the inner, and I'm going to change the order just so it's really obvious. This is 5 times 7i. Well, there's a minus and there's a plus. I have to add these to combine them. The outer and inner always combine to make 0. So you don't even have to do it if you want, just for the fun of it. 5 times 7, 35. It makes you feel good to do math sometimes. If you're that person, you can do them, but you don't have to because they always go away. All you have to do is take the first number, 5, square it, 25, and then say it a couple times. 25, 25, 25. It's in my mind. And then look at the other number, 7, square it, 49, plus 25. Well, 49 is 1 less than 50. 50 plus 25 is 75. 1 less is 74. So here, 25 plus 49 is 74. And I'm done. And I didn't have to do most of these steps. I squared 5, I squared 7, I added them up, I'm done. What's the advantage here then? The advantage is that this is always a real number. Notice that the imaginary part, the part with the i's in it, the part with the square root of -1, is gone. This is comfortable because your grandmother, everybody understands 74. If you say 74, she can count to 74. If you say, Granny, count to 5 plus 7i, she's going to have struggles with it. So this is why we want to use this conjugate, because we're trying to get a real number that we can work with. Let's work one more problem together. This is an example of dividing two complex numbers, and this is as difficult as it gets with complex numbers. The fun part of this is you can't actually do it. There would be no sensible way to write this out as a long division problem and to try to get an answer. It turns out mathematically there is a way to simplify this which takes care of the division for us. And it uses these complex conjugates that we just talked about. So the secret here is look at the bottom of the fraction, and whatever it is, write its complex conjugate. So here's a plus. I'm changing the plus to a minus. 3 plus 4i turns into 3 minus 4i. And then, to be fair, if we're doing something to the bottom of this fraction, we need to do the same thing to the top of the fraction. So we're multiplying by this over this. We're multiplying by 1. We're not changing the value, but we are greatly simplifying it. So here we go. We will use our FLOI technique. We'll use that little secret we learned last time on how to do complex conjugates by adding up the two squares. The top will have to do a little bit of work, but it'll still be simple. Let's start with the bottom, the denominator of the fraction. I look at the 3 and I square it. 3 times 3 is 9. I got that. 9, 9, 9. I say it a couple times to fix it in my memory. And then I look at the 4. 4 squared is 16. 9 plus 16, I'm thinking 25. And I'm done with that. And I didn't have to write anything. This looks very, very impressive. Now, the top, and I'm going to FLOI it. So my first is 6 times 3. I need to say this in my mind. 18, 18, 18, 18. Okay, I'll remember the 18. Here's a 5 times 4. That's 20. There's a negative. It's negative 20. Remember, this last term always gets flipped in sign because of the I squared. And so I had a negative 20. I'm turning it into a positive 20. I have the 18 still in my mind. 18 plus 20. I'm going to write 38. And then the outside, 6 times 4 is negative 24. Say it a couple times. Negative 24, negative 24, negative 24. I've got that locked in. And then 5 times 3 is 15, 15, 15, 15. 24 minus 15 is 9. The 24 was bigger. Its sign was negative, so my 9 is negative minus 9i. And this isn't the answer anybody wants. The reason is this answer doesn't look like a complex number. It doesn't look like a plus bi. It looks like something, something that looks like a complex number. But then it's part of a fraction. And so what the scientists and engineers especially like to do is they split up the terms of the numerator. So we have a 38, and we put that over the 25. And then we have a minus sign, and we have the 9i, and we put that over the 25. And then just to put the real icing on the cake, they write it in a form that definitely looks like a complex number. They put this minus, and here's the fraction. It becomes a coefficient. before this I. Now you can see A plus BI, and there's an A part and there's a B part. The scientists and engineers like this because a lot of times when they solve a problem and they get a complex result, they want to know the real part because they can do something with that. And the imaginary part they do something else with, or they just throw it away. It depends on the application. But there's your answer, and you see by using the shortcuts, the foiling, the FLOIing, the sum of squares shortcut for complex conjugates, this was actually a really simple problem. Keep practicing these. You get good at them by doing a lot of them. If the first couple times you fail, that's all right. Everyone fails the first couple times. Keep working at it. You'll get good at it. It'll make taking tests and quizzes faster and easier. Thanks.